Every journey to conquer space begins right here, with the most refined and purest dust particles found deep beneath the Earth's surface today. The sunrise reflects off the towering steel silos as our journey starts at this state-of-the-art industrial complex dedicated to advanced material science. Our guide is Dr. Nam, a leading expert in materials who will show us how raw minerals are transformed into aerospace-grade heat-resistant ceramic masterpieces. He begins by sampling ultra-pure white powder, where even the slightest contamination could compromise the integrity of a $1 million rocket engine component later. The requirement is extreme purity, reaching 99.99%, ensuring that the chemical composition remains stable under the most intense thermal stress. Beside alumina, we use silicon carbide, a material known for its incredible hardness and ability to withstand temperatures that would melt most common metals. Robotic logistics systems ensure that materials are moved through the facility with surgical precision, maintaining the sterile environment required for high-tech ceramic production. Under the microscope, we can see the raw potential of these crystals, waiting to be ground down into the building blocks of future spacecraft. Dr. Nam verifies the crystal structure against aerospace standards, ensuring that every batch of raw material meets the rigorous demands of deep space exploration. The sheer scale of this operation is breathtaking, as tons of specialized minerals are processed daily to fuel the rapid growth of the global aviation industry. The air filtration system hums in the background, keeping the atmosphere dust-free to prevent any foreign particles from entering our sensitive ceramic powder mixtures. Every sample is meticulously tracked, creating a digital footprint that follows the material from the raw mine all the way to the final flight. With the raw minerals approved, we move deeper into the heart of the complex, where the first major physical transformation of the material occurs. Modern alchemy begins here, where heavy machinery and precise chemistry work together to break down the minerals into a state of ultimate fineness. Precision is the law in this laboratory. Even a fraction of a gram off could alter the final material's resistance to thermal expansion. By understanding the atomic bonds of these minerals, our engineers can predict how they will behave when subjected to the extreme heat of re-entry. The raw materials are now ready for the next phase, entering the massive mixers where they will be blended into a perfectly uniform slurry. This dust is the foundation of our technology, each grain a tiny warrior that will soon help a rocket survive the vacuum of space. As we conclude the mineral preparation phase, the true engineering challenge begins, turning these loose powders into a solid, unbreakable structure of power. The ball milling process is intense and loud, as thousands of high-strength ceramic beads crash together to crush the minerals into nano-sized particles. These beads must be harder than the material they are grinding, acting as tiny hammers that work for 48 hours without a single break. He ensures that the friction doesn't overheat the mixture, as maintaining a constant temperature is vital for achieving a uniform particle size distribution. Our goal is a particle size of 0.5 microns, which allows for maximum packing density during the later stages of the forming process. The mixture now becomes a slurry, a thick liquid that must be perfectly homogeneous to prevent any weak spots in the final ceramic product. This blending process ensures that the alumina and silicon carbide are evenly distributed, creating a material that is consistent from the core to the surface. Specialized organic binders are added, acting as a temporary glue that will hold the particles together before the final high-temperature firing process takes place. We mix under a vacuum to remove all air bubbles, as even a tiny pocket of gas could cause the component to explode under pressure. The slurry is then pumped into this massive spray drying tower, where it will be transformed back into a dry, granular powder for pressing. The nozzle atomizes the liquid into millions of tiny droplets, which dry instantly in the hot air to form perfect, hollow spherical granules. These granules are the secret to a smooth flow, allowing us to fill complex molds evenly without any clumping or uneven distribution of material. The powder now flows like water, a critical property for the next stage of automated production where speed and consistency are paramount for success. Moisture levels are checked repeatedly, as any residual water could interfere with the bonding process and create defects in the ceramic's internal structure. Quality control is continuous, Every batch is verified against the master specifications to ensure total compliance with international aerospace standards for safety. This facility operates 24 hours a day, processing the materials that will eventually become the heat shields of the next generation of spacecraft. The infrastructure itself is a marvel of engineering, designed to be easily cleaned and maintained to prevent any cross-contamination between different material grades. Digital twins of our machinery allow engineers to monitor the flow of material and predict maintenance needs before any downtime can occur in production. Cleanliness is as important as the chemistry itself, and we follow strict protocols to ensure that every machine is sterile before a new batch. The powder is now ready, its physical and chemical properties perfectly tuned for the high-pressure shaping process that will give it a solid form. To prevent any moisture absorption from the air, the powder is kept in vacuum-sealed bags until the very moment it is needed for pressing. Every minute counts in this high-stakes environment, where the deadline for a satellite launch might depend on the precision of our ceramic components. We now enter the arena of power, where massive machines will apply hundreds of tons of force to turn powder into a solid object. The cold isostatic pressing hall is a place of immense force, where materials are squeezed from all sides simultaneously to achieve perfect density. The powder is first loaded into custom-designed rubber molds, which act as a flexible skin that allows the pressure to be applied evenly everywhere. A perfect seal is critical. Any leak of the hydraulic fluid into the powder would ruin the batch and damage the expensive ceramic material inside. The mold is submerged in a liquid-filled pressure vessel, which will soon become the medium for transmitting incredible amounts of mechanical energy to the ceramic. The lid locks down, sealing the chamber. Inside, the environment will soon mimic the crushing pressures found at the bottom of the deepest oceans. As the pumps activate, the sound of high-pressure fluid filling the lines echoes through the hall, signaling the beginning of the consolidation phase. Pressure climbs rapidly to 200 megapascals, or nearly 30,000 pounds per square inch, forcing the particles to lock together at a molecular level. This is isostatic pressing, where the force is identical from every direction, ensuring that the finished block has no internal stresses or weak points. The equipment must be incredibly robust to contain such power, and our machines are inspected daily to ensure they can handle the constant stress. Dr. Nam monitors the rate of pressure increase, as a curve that is too steep could cause micro cracks in the fragile green body being formed. Decompression is a delicate process. We lower the pressure slowly to allow the material to stabilize before it is removed from the high-pressure environment. The mold emerges, and what was once a bag of loose powder has now been transformed into a solid, chalk-like object known as a green body. Carefully, the mold is removed. The part is now solid enough to be handled, but it is still relatively soft and can be easily broken. Dimensions are checked with sub-millimeter accuracy using laser tools, as the part will shrink by a specific percentage during the later nung process. Even though it looks strong, the green body is vulnerable. It must be treated with extreme care before it goes through the final fire transformation. The surface is a testament to the quality of the powder and the evenness of the pressure. A perfect blank canvas for the final sintering. Cleaning the part before nung ensures that no external dust is fused into the surface, which could create a point of failure under high stress. A silent army of future aerospace parts waits here, each one representing hundreds of hours of research and thousands of pounds of applied pressure. The beauty of industrial engineering is visible in these simple forms, which will soon become the most advanced heat shields ever made by man. The pressing stage is successfully completed. Now, we prepare for the most dangerous and critical step of all, the high-temperature sintering furnace. The temperature is about to rise. We are entering the Hall of Heat, where the ceramic will find its true strength and final identity. This is where the magic of thermal bonding happens, turning a fragile object into a material harder than any steel known to modern industry. The sintering process is fully automated. A high-precision robot places the foil into the furnace, ensuring it is positioned perfectly for even heat distribution. The chamber is sealed and a vacuum is pulled. Removing air prevents oxidation, which would degrade the ceramic's performance at extreme aerospace operating temperatures. The heat starts to climb. In this phase, we will push the material to its absolute limits, far beyond what any earthly environment could provide. At 500 degrees, the organic binders begin to burn away, leaving only the pure ceramic particles to face the oncoming heat alone. 1000 degrees, the material is now entering a state where its atomic structure becomes mobile, preparing for the final bond that defines its strength. As we reach 1500 degrees, the individual grains of alumina and silicon carbide start to fuse together, eliminating the spaces between them forever. This is sintering. The atoms migrate across grain boundaries, merging the powder into a single, dense, and incredibly hard solid block of supermaterial. 2000 degrees Celsius. This is hotter than the surface of some stars, a temperature where most metals would have turned into liquid or gas. Dr. Nam knows that at this temperature, the material is undergoing a total metamorphosis, gaining the properties needed to survive a rocket's engine blast. The part is now white hot. It must hold this temperature for 12 hours to ensure that the crystallization is complete and the density is perfect. Massive amounts of electrical energy are converted into heat through induction, providing the clean and precise thermal control required for high-tech aerospace manufacturing. After the soak time, we introduce argon gas. This inert atmosphere protects the ceramic and helps manage the cooling rate to prevent any thermal shock. Cooling must be slow. If the temperature drops too quickly, the internal stresses could shatter the ceramic into 1,000 pieces before it even leaves. Large cooling systems work to remove the heat from the furnace body, a process that takes as much engineering as the heating phase itself. The chamber returns to normal pressure. Inside, a new material has been born, one that is ready to face the vacuum and the fire of space. The foil is removed. It has changed color to a dark, matte gray and has become significantly smaller and much more dense than before. Even after hours of cooling, the part still retains significant heat. We use thermal imaging to ensure it is safe to handle for the next steps. Listen to that sound. The high-pitched ring indicates a perfect, dense structure with no internal cracks, a sign of a successful sintering process today. The material must now rest. This stabilization period allows the microscopic crystal structure to settle before the final machining and grinding operations begin. Maintenance is key. Every firing leaves a mark, and we ensure the kiln is perfect before the next set of aerospace components enters the flame. Success in the furnace is a team effort. It's the culmination of chemistry, physics, and years of engineering expertise coming together in a single part. This material is now harder than any metal. It is ready to be carved into its final, complex shape using the only thing that can: diamond. The fire has done its work. From powder to stone, from earth to the stars, the journey of this high-tech ceramic continues to the machine shop. We track every kilowatt of energy used, optimizing the process to be as sustainable as possible while maintaining the highest levels of material performance. Each part is unique, given a permanent identity that will stay with it from the factory floor to the edges of the Earth's atmosphere. We move now to the final stage of shaping, where precision meets the hardest substances on Earth to create the ultimate aerospace geometries. Only diamond can cut what we have created. This phase requires the most advanced CNC technology to achieve the tolerances required for supersonic flight. The parts are loaded into 5-axis machines that can carve complex curves and deep internal channels with a precision of just a few microns. High-pressure coolant is essential to wash away the ceramic dust and keep the diamond tools from burning up against the incredible hardness of the part. Even underwater, you can see the sparks. The resistance of the material is legendary, making it the perfect choice for the hottest parts of engines. We use specialized diamond wheels to achieve a surface finish so smooth that it minimizes air resistance at speeds faster than the speed of sound. The programming is an art form itself, calculating the exact path to remove material without ever putting too much stress on the ceramic structure below. We compare the real-time cutting data to the original digital design, ensuring that any tool wear is compensated for instantly by the smart software. After machining, the parts are cleaned in an ultrasonic bath. High-frequency sound waves reach into every microscopic crevice to ensure the material is perfectly clean. Inspection is the final gate. Every dimension is measured by a coordinate measuring machine to ensure the tolerance is within 0.005 of a millimeter. X-ray imaging allows us to see inside the solid stone. We look for the tiniest flaws that could grow into a crack under the stress of launch. Ultrasonic waves travel through the part, echoing back any hidden defects. This non-destructive testing is vital for ensuring the life of every aerospace component produced. At 50,000 times magnification, we see the true beauty of our work, a landscape of perfectly interlocking crystals that provide the material's strength. Fluorescent testing makes even the smallest surface scratch visible as a glowing line under ultraviolet light, ensuring that only perfect parts move forward today. We map the entire surface in 3D, creating a digital birth certificate for each component that includes every measurement and test result for future reference. The final touch is manual. A skilled technician polishes the part to a mirror finish, reducing friction to the lowest possible level for maximum fuel efficiency. This lab is where we prove our promises. Here, the raw materials we saw earlier are officially certified as aerospace-grade technology ready for the sky. The paperwork is as precise as the part itself. Every component must be accompanied by its data to ensure total traceability throughout its operational life. It is a masterpiece of modern engineering. What started as simple earth and dust has become a jewel of the aerospace and defense industry. For Dr. Nam, this is more than just a component. It is the result of thousands of hours of work and a symbol of human ingenuity. These parts will soon be shipped across the globe, joining the engines of the world's most advanced planes and the rockets of the future. Transporting these components requires as much care as making them. We use custom containers to protect them from any vibration during their journey to assembly. The destination is the launch pad. From the deep mines to the high heavens, this ceramic is ready for the ultimate test of its performance. The shipment departs. Our factory has done its job, and now the material must prove its worth in the harshest environments known to mankind. Inside the jet engine, these ceramics will operate in temperatures that would melt any metal, allowing engines to run hotter and much more efficiently. The integration is seamless. Our ceramic technology is the heart of the engine's thermal management system, protecting the most critical components from destruction. When a spacecraft re-enters the atmosphere at 20 times the speed of sound, our ceramics are the only things standing between the crew and disaster. The material holds strong. In the blast of a rocket engine, the silicon carbide remains solid, its properties unchanged by the violent thermal environment. Seeing the technology in action is the ultimate reward. Every successful launch is a testament to the hard work done right here in this plant. It is a symbol of our commitment to excellence, a piece of the future that we have brought into the present through science and sweat. We are also building the next generation of engineers, inspiring them to look at a grain of sand and see the potential for a starship. The work never stops. As one batch leaves, another begins its journey, starting once again with the selection of the purest raw mineral powders. This is the pinnacle of industrial harmony, where human creativity and robotic precision come together to push the boundaries of what is possible in space. As the day ends, we look toward the horizon, knowing that our materials are already up there, orbiting the planet and exploring the unknown. Our name is synonymous with quality and innovation, a brand that the world's leading aerospace agencies trust with their most important and dangerous missions. From dust to density, from heat to hardness, we have seen the incredible transformation that makes modern space travel possible for all of humanity. He leaves with the knowledge that his work has reached the stars, a legacy written in ceramic and fire across the dark canvas of space. That trail of smoke is our success story. It is the proof that when we combine minerals with mind, there is no limit to our reach. Thank you for joining us on this journey from the ground to the stars. The future is being built today, one ceramic grain at a time. Stay curious, stay inspired, and keep looking up. The journey of high-tech ceramics is just beginning, and the best is yet to come for us.